Okay, so this is the end of the very last lecture of the course, and it's time to wrap up. So let me say a little bit about where you can go from here. Or let me put it another way. Let's talk about what are the topics we actually didn't cover in this class. So one of the most important topics we didn't cover is quantum error correcting codes. Now, quantum error correcting codes were a major discovery of quantum computing. These came as a major surprise to physicists because it was believed that quantum systems just could not be protected from the environment, that environmental decoherence was inevitable. And yet, what a quantum error correcting code does is this pretty remarkable thing. So let's say you start with some quantum state psi. What you can do using a quantum error correcting code is you can transform it into a longer state, state on more qubits. Call it E of psi, some encoding of psi. And now, let's say that over time, some of the qubits in this encoded quantum state decohere, so they are measured by the environment. So now what do you do? Well, because this was a quantum error correcting code, what you can do is you can now start with some fresh qubits. So these are qubits in the state 0. So these are many qubits which are all zeros. And you would apply some decoding circuit. So now you'd apply some circuit U to it, which is an error correcting circuit. And what does this do? Well, what it outputs is the quantum state E of psi. So the errors all get wiped out. But remember, the circuit U is unitary, so it cannot erase any information. So where does the information about these errors go into? Well, it goes into these clean qubits that we input. So this is information about the error locations and the types of errors. Okay, so the way to look at it is we had our qubits and in this error corrected format, and then environmental noise, environmental decoherence happens, and because it's adding entropy into the system, it's as though it heats up this quantum state. What you do, you input also some clean qubits. These are cold qubits. And then you take them through quantum error correction, which cools down the state that you were trying to protect, this state. And instead it heats up, it transfers the heat into these clean qubits, the cold qubits that you had input. These you now discard, and you've effectively cooled your original qubits back down into the quantum state that they were supposed to be. Now, of course, this is a quantum error correcting code, but what we'd like to do is actually perform computation on qubits while decoherence is going on, and this is called fault-tolerant quantum computation. These are beautiful, really, really a beautiful theory, and this is something that, of course, is essential to implementing quantum computers. Now, the other kinds of topics we didn't cover are more advanced algorithms. We didn't cover, algorithms like phase estimation, and there are quantum walk-based algorithms. Okay. We also didn't cover quantum cryptography, which provides a way of recovering from the damage done by quantum algorithms, in the sense that, since quantum algorithms break most classical crypto systems, quantum cryptography is a way of using the specific properties of quantum mechanics to actually implement secure crypto systems. And then, of course, the other thing we didn't have time to talk about is what's the state of the art with respect to experimental realization. And finally, there's this growing interaction between quantum computation and various parts of physics. So for instance, one of the most active areas today is this interaction between quantum complexity theory and condensed matter physics. And it's this area that's being called quantum Hamiltonian complexity. So these are all, these are just some of the areas that you can move on into. Let me also mention a few topics that are closely related to things that we did cover in the course. So for example, early in the course we talked about teleportation. It turns out that you can actually use teleportation in order to carry out quantum gates and quantum computation. And this is a very important idea which plays a role in many, many aspects of quantum computing, including in some of the most efficient ways of doing fault-tolerant quantum computing. Then there are a couple of topics which has to do with which is related to the Bell inequalities, or the CHSH game that we saw for testing quantum mechanics. And it turns out that this CHSH game can be used to build a random number generator where you can certify that the output is random even though you don't trust the actual random number generator. So meaning you certify that that actual output, the particular output that you got was really random. And similarly, there are ideas about how you can actually test whether a quantum computer that somebody actually tries to sell you. So somebody claims to have realized a quantum computer in the lab, and you want to test it. Well, how do you test it? How do you test that what it's outputting, which is supposed to be, it's solving some problems which are extremely difficult to solve classically. So how can you, as a classical entity, actually test that this computer behaves as claimed? Well, it turns out that the CHSH game has a lot to do with how you can actually carry this out. So what I'll do is I'll actually give you pointers to some of these topics in case you're interested. So those of you who are interested, you can follow up and read about these things. Okay, so now let me say a little bit about in our last survey we had asked you for feedback on this course to help to help us design, to help us improve this course in the next iteration. And actually your feedback was extremely useful. So there were a number of takeaway points we got from there. One is that there are ways we can do a better job of helping you deal with the math background for this course. So in other words, we should be able to provide some background material for the basic linear algebra and make that available, say, a couple of weeks before the course actually starts, so that people can actually get a better idea about whether they have the background to take the course, and if they do, to brush up on it and so on. A second thing that came out is that it should be possible to use the discussion forum in a more meaningful way. The discussion forum is really a key to this course, and actually another aspect of this is that the edX platform is really evolving a lot at this point in time. This is a great thing in the sense of where it's going to, and actually it'll be in that place fairly shortly, within the next month or two. One of the things that's going to be greatly enhanced in this process is the discussion forum. But we also understand that it should be possible to use the forum in more interesting ways. Many of you talked about expanding the topics that can be covered in the course. I actually listed some on the previous slide. And some of you asked that we should provide you with pointers to research questions. And this is, again, an excellent suggestion. This is something I'd actually meant to do in this run of the course, but there's only a finite amount of resources, going into it, and hopefully by the next iteration we'll be able to do this. I should say that based on your feedback and our thinking now, and based on the rest of the course, we'll hand out one more survey, and again, this survey will be cumulative in the sense that we'll add on a few more questions to the existing survey, and you should just answer the new questions. And again, this will be invaluable to us in terms of where we move to in the future. Now, let me say one more thing about the course, which is putting up a course like this takes a lot of work. And in fact, a lot of the work in this course was done by Sweng Wu. Sweng Wu is my graduate student. He's doing a PhD with me in quantum computation. And basically, all the work that he has put into this course is just out of, because out of a belief that, making this kind of course available to anybody, anywhere in the world is a very important thing. So I should say that Sweng Wu put in an incredible amount of work into this course, into this, into this course. Both in designing the course, in coming up with, for instance, the homework questions, but also in dealing with this evolving platform on edX, which took an incredible amount of time and effort. I should also mention that there were two tiers for the course, Anil Das and Simon Stevenson, who spent a lot of effort on the discussion forums, which I believe are the lifeblood of the course. So again, if you enjoyed the course, you really owe these people a vote of thanks. Okay, so this brings us to the end of our journey. Even beyond the surveys, we'd love to hear from you, to hear about your thoughts about the course, how you felt about it. Please feel free to use the discussion forum to tell us about it. And we really hope you enjoyed it. Thank you.